Hello students, I am Joan from the Department of Physics. Today, before entering into our topic, I want to give you something. Let me take it from the wallet. Don't feel that I am going to give the money since we are supporting the cashless economy. I want to show you my debit card or a credit card and ATM card. You can see this ATM card. I am not going to speak anything about the ATM card and the similarity of all the cards which is in the back side. And what you are seeing here, that is a black line, a black stripe. What it is? Does the manufacturer like this black color? That is why he put it on all the cards. No. That is the physics behind on this black magnetic stripe. So, at the end of this video, you will be getting a fruit from me. So, please stay to listen the beautiful topic, Motional EMF. In this topic, I am going to imagine a rectangular shaped conductor. The speciality of this conductor is having a movable piston at the end of the conductor, and this conductor is being placed in a magnetic field. And the length of the conductor we are going to assume as L. The speciality which I already mentioned is capable of moving. This conductor, a rectangular part over here, is capable of moving up to this much distance. Yes, of course, it can move up to this much. So that distance we are going to consider as x. And the total setup we are going to name it as PQRS. In this conductor, as I already told, L is the length and x is the distance of the conductor can move in the magnetic field, and one more thing, if the conductor is being placed in it, it is capable of moving also in the magnetic field. So the velocity that in which it projects is v velocity. So you can assume that it is traveling in a v velocity inside the conductor. So these are all the main things, and before entering into the derivation part, I want to give you some few tips, very interesting basic concepts. First one is flux, and the second one we are going to use is Faraday's law. Along with that, Lenz's law. Also, Fleming's right hand rule. And finally, we are going to find what is EMF here. Before entering into this topic, we need to know these basic things that will help you to understand the EMF concept very well. Okay, so here we'll begin with the flux. What is the meaning of flux? Flux is, here we have the rectangular shaped conductor. It has a certain area, and this magnetic field that we have is always represented in a circular lines as we have the basic understanding. So here the magnetic field lines in the field is of circular lines. So in a particular area, how much amount of lines are flowing, that is called as magnetic flux. We have the conductor over here. This conductor occupies an area. On the area, how many number of magnetic lines are flowing, that is called as magnetic flux. So that magnetic flux we can write in an equation form as pi in terms of B magnetic. So pi B is equal to magnetic field and it occupies certain area. So why I am writing dA instead of writing A? Why I have written dA? So this conductor, a movable piston, is capable of moving in that. So once it is started moving over to this direction, the area will be keep on reducing. So the area is a changeable one. So here this area has a formula, length into breadth. As we already know, the rectangular formula, rectangle has a area formula of length into breadth. Here the length we already know as L and the breadth we already know as X. So I will be rewriting this equation, flux equation, as B into L into X. This is the value of magnetic flux to the rectangular conductor that we have in a rest bench. So our flux part is over. Now next thing, here I already told it at the initial condition, the flux. This is the initial condition of the flux. Now once the conductor started moving, once it is moving towards this direction, the area will be reducing. So once the area will keep on reducing, that is a change in magnetic flux. So that change in magnetic flux will induce something that is explained by Faraday's law. So what does the law is saying? Faraday's law is saying change in magnetic flux. What is a change in magnetic flux over here? As we already found out the flux at the initial condition, now the conductor is moving, flux is changing. Changing flux with respect to the time. Always the flux will be changing with respect to time. So if I am writing flux, we already know IV, and it is changing with respect to time, that I can write it as dV by d pi v by dt. So this is a change in magnetic flux. It is going to produce something. So how I can understand what it is going to produce? I can understand once the conductor started moving towards this direction, we are going to use this Fleming's right-hand rule to understand what is going to gain extra. So it is moving towards this direction. Definitely there will be a reduction of area and there is a change in magnetic flux. So change in magnetic flux will induce a force that is called electromotive force. EMF we will call it as. That EMF will generate over here. What is the purpose of generating EMF? Once we started moving, the alignment in the conductor, once the conductor started moving, the charges alignment will be like positive will be upwards, negative will be downwards. The force that we are receiving will make the charges up and down motion. Once the positive charges are up, that will be able to move towards a current in this direction. So once these charges are up, that is a potential difference between the two ends, that we call it as EMF or in terms of voltage. So the EMF which will generate, what it will do? It will pass the current inside the closed loop conductor. This is a closed loop conductor, so the current flow will be like this direction. So there will be a flow of current. It means because of the movement of this charge alignment to up to down, it will induce a force that is called electromotive force, that is EMF. So why introduce this Fleming's right hand rule? What did it say? You stretch your right hand, the fingers of thumb finger and index finger and middle finger. You stretch mutually perpendicular of each three. Once you stretch this finger, then you can apply it over here. Here the charges are getting the force to make positive up, and already the direction of magnetic field is this, and the current will be towards this direction. So we can understand from this Fleming's right hand rule, direction of magnetic field pointing the index finger and the middle finger point towards the current direction, and the thumb finger shows the force which is in the conductor. So this we understood, and now here coming back to here, the change in magnetic flux is produced, change in magnetic flux induces the EMF, and here we are going to use this just add only one more negative symbol. What does it mean? Why we have this negative symbol arises? That is explained by Lenz law. So what does the Lenz law say? In your 10th classes, you have studied the experiment which is called electromagnetic induction. That in which what is going to happen? Here we have the coil which is connected to the galvanometer and a magnet with the north-south and north-south poles that is coming towards the coil. When it is coming towards the coil, what will happen? You will experience a deflection in the galvanometer, and the direction of the deflection only matters. What it is doing? Once the magnet is coming closer to the coil, the deflection will be showing away, this side. Once the magnet is going away, and the deflection will be this side. So you can experience, based on the movement of this magnet, the directions are opposite. So we can come to know from the Lenz law, EMF is always opposing the cause which is produced. So who is producing the EMF? Change in magnetic flux. So obviously the EMF will oppose the change in magnetic flux. Now we can name this equations as 1, 2, 3. Now you can fastly substitute this value of this magnetic flux into this equation. So if you are substituting that, so EMF is equal to minus d phi v by dt. So there we are going to substitute the value of phi v, and it will be d by dt of b into L into x. Here you can know this b and L is not varying over here. Only the variation in the distance. So if the distance are varying, you can take all the constant thing out and you can write only the variable things in terms of differentiation. So only this dx by dt only the variable term. So here, if you are taking this dx by dt, we already know it is velocity. Once the distance is changing with respect to time, that we call it as velocity. So here, the direction of velocity is opposite to the direction of magnetic field. So we will be writing it as minus v. So the final equation will be as, here minus and minus in the same equation. So it will be making as plus. So you will be getting the EMF in this as v into L into v. This is the EMF which is produced in the rectangular coil. And here B is the magnetic field, L is the length of the conductor, and V is the velocity of the conductor. Now come back to the initial case which I told about the magnetic stripes. So what is this? These are magnetic stripes. What we used to do by using this nowadays, a digital payment of swiping. While you are swiping this, it will be acting as a magnetic field. Here you can consider this as a north pole and this is a south pole. When two poles are there, there will be a magnetic field exists, and this magnetic field, when it is traveling on the electric machine, it will become a closed loop. Once the loop is closed, the current will started flowing through it, and that current is inducing to access your details on the pavement. So this is the thing that you understood from today's class. Even you can also calculate how much EMF is being produced by using this formula. So it will be around 7.25 volt in an average. So think everything with respect to physics on your day-to-day life.